Good evening. Welcome to this class of analytical chemistry, where we are discussing about the chemical equilibrium. And why we are talking about this chemical equilibrium, because two things of that particular equilibrium, that means its properties and concept, will be utilizing in future for the particular type of analysis. So, we have the equilibria and that particular equilibria, what we are talking about in terms of very simple reaction, what we all know, that the corresponding reaction of water with that of H plus, that means the proton forming H3O plus. So, any other type of solvent where you can have the lone pair of electrons on oxygen atom of this H2O molecule, that means water molecule. So, this is a particular thing, that means H plus, that means one single electron is also not there. So, if it can form some interaction, that means the coordinate bond, that we all know that a lone pair of electrons when utilized, that means it can be donated to some other species which is positively charged, which is devoid of electron, such that we call in terms of the corresponding coordination compounds when the water is bound to Mn plus. Similarly, this H plus can also bound to this water molecule, giving rise to H3O plus. So, there are several consequences of all these things, that means when we form this H3O, how this particular species is forming, and this we all know that this particular proton where the source is, that means the acids, and we are talking about the different acids, and we exposed yourself that in one particular case we have the corresponding strong acid case and in another case the weak acid case. The how these two things, that means they are basically why this we are talking, this is because this H plus, these acids, that means strong acid or weak acid, can provide these protons as they are good proton donors. So, what we are seeing so far, that when these two are reacting, so one particular example what we are talking about is not only the interaction of the corresponding only proton to water molecule, but if we consider it as that H2O, and instead of talking in terms of H plus, we can consider this another water molecule. So, one of them, that means one of the water molecule can function as a base and another can function as an acid. So, there will be an acid base equilibrium. So, this equilibrium is a typical acid base equilibrium. So, the water molecule what we are considering as acid can donate the electron. So, the proton. So, the donation of that particular proton is coming from this water molecule and is going from this to this base. So, this base will be now H3O plus, and it will the base remaining from the acid 2 is the HO minus. So, what we discussed in the previous class, that this is the corresponding conjugate base. So, H2 will giving you the corresponding conjugate base, which is hydroxide ions. Similarly, this base what we are considering is accepting the proton, giving you the corresponding conjugate acid as H3O plus. Similarly, two molecules of methanol can also behave in a similar fashion, and one of the methanol molecule can be a proton donor and other can be the proton acceptor. So, by definition one of them can be considered as an acid and other can be considered as a base. So, these things we have discussed so far, that amphiprotic protons or the autophotolysis or self ionization can take place on water as well as the water like methanol molecule. So, these two things, that means if we can have other proton donors, so how good the proton donor is and how weak or strong the proton donor is. So, the strong acids, if we consider the strong acids, what we will consider or focus our attention that the corresponding dissociation reaction. So, if we have a corresponding acid as HA, and when we go for talking or realizing the corresponding chemical equilibrium in terms of the corresponding HA dissolved in aqueous medium, whether you will have a type of dissociation like H plus A minus, that we will try to see, and how far this equilibrium is going from left to right or from right to left. That means, what percentage of HA is getting dissociated between H plus and A minus. That will also tell us that how much of this H plus is being provided to the solution after dissociation. So, if we consider some other acid, we all know that typical hydrochloric acid, that means the aqueous solution of hydrochloric acid, if it dissociates like H plus and Cl minus, and if the dissociation is going from left to right almost completely. So, 90 or 90 plus or 99 plus percentage of dissociation can take place in water medium. So, this is the medium is the water. So, this can happen that you can have large amount of this supply of H plus, and this particular one can give rise to the amount of H which is originally bound as or in the corresponding form in the gaseous hydrochloric acid. We all know the aqueous solution is your corresponding acid where the dissociation can take place, and if all of them almost give you the H plus, whatever number of H you can have is available from the HCl molecule itself. So, if the dissociation is very large and there will be a complete almost complete dissociation, we can label this as a strong acid. But what about the weak one? The weak one will not go like this. So, weak one will not dissociated in that particular fashion. So, by definition we can consider it as that strong acid dissociates completely, whether the weak acid does not. So, a tendency of the solvent. So, we are bringing now the involvement of the corresponding solvent. That is why I just now told you that your HCl, it is a gas, and when it is dissolved in water molecule, water solvent, water is your solvent, it can function as a very good acid. So, this particular solvent, where we are discussing this from this very first part of this particular slide, that you have these two water molecules, and all we know that water molecules are very good solvent molecules. Similarly, this methanol, the CH3OH molecules are good solvent molecules. So, how solvent can play some important role over here during this donation and acceptance of these protons. So, the tendency of the solvent to accept or donate protons determine the strength of the acid and the base. So, what you see that you have a medium, and that medium playing some important role, that such that your water medium, if it accepts the proton. So, if we bring this water molecule over here and if it accepts water, so that will give rise to H3O plus. So, water can play some dominant role for accepting that particular H plus. So, if you have another water molecule, as I know this H plus is coming from the another water molecule. So, this formation of this H3O plus and the amount of H3O plus forming over there will tell you how strong your acid is. But in case of the weak acid, this kind of dissociation or this much amount of H plus will not form. So, the equilibrium again plays some important role for the strength of the acid and the strength of the weak acid as well. So, what we get in water, again the medium is water. These two acids we are now comparing. Just now we have seen it is hydrochloric acid, and another acid we are considering now is your perchloric acid, HClO4. Again both of them are monoprotic acid, because the formula of hydrochloric acid we all know that is HCl and another one is HClO4. So, in water medium they both of them are leveled. So, that means you have complete dissociation, that is water molecules are functioning in a nicer way to accept protons from both the hydrochloric acid, then aqueous hydrochloric acid or aqueous HCl, as well as aqueous perchloric acid. But if we think that there is anhydrous acetic acid, so acetic acid itself, it can also function, because wherever you have the oxygen and the hydrogen. So, in acetic acid medium, this is, we all know, this is weaker corresponding weaker proton donor, that we will consider that what is your weak acid. So, weak acid is nothing but your acetic acid, and this particular equilibrium is not moving very far towards the right hand side. So, we will get very few or very less amount of H plus from this particular medium, but remember, in all these cases we are talking about aqueous acetic acid. Now, for this particular type of leveling effect, what we consider that anhydrous condition we are trying to think of. So, what about in case of the corresponding anhydrous condition? That means no water molecule is present, and these water molecules, whatever they are showing their typical affinity or the function toward this particular proton, will not be shown by this kind of acetic acid. So, in anhydrous acetic acid, which is a weaker proton acceptor, none of them, that means the perchloric acid as well as hydrochloric acid, will not dissociate completely. That means, we are tampering, we are just interfering the corresponding acidity or the strength of the corresponding acids, that means the perchloric acid and hydrochloric acid. So, if they do not dissociate nicely, or whatever amount of dissociation we find for water as the solvent, we cannot consider these two acids as the strong acid in anhydrous acetic acid medium. So, this is a very important area of thinking and an important area of knowledge. So, where we consider something, that means all these reaction conditions, the equilibrium and all other things can change also when we go for anything which can be tagged as non-aqueous solution. Okay. So, this non-aqueous solution. So, how we can think of this non-aqueous solution is very simple, that we will not have water over there. So, anything which can be liquid, that means if we have liquid carbon dioxide, liquid sulfur dioxide and other things which can function, we all know that which can function as a solvent. Similarly, this anhydrous acetic acid, can be considered as another non-aqueous solution, where we try to get or try to involve the corresponding equilibrium, that means the chemical equilibrium, what is happening and how it can function for these two acids, one is HCl and another is HClO4. Okay. So, these are the things, that means how solvent can play some important role as the basis for this dissociation reaction. Okay. So, whatever reaction we are thinking of and we are talking about all these things, so is HClO4. So, if the proton is moving, so this is not ClO2 minus, it is ClO4 minus, sorry, this is not ClO2 minus. So, this is the perchlorate anion is moving. So, only this proton is moving from COH to COH plus. So, this thing we are not getting. So, that is why in this particular medium your perchloric acid only. So, perchloric acid will be stronger in this particular solvent medium. So, if the perchloric acid can show dissociation in any other medium apart from our water medium, we can consider them as a good acid if only you have the corresponding dissociation. So, a particular type of equilibrium state we are considering, and how this equilibrium state will be discussed in terms of any other typical example. So, any chemical equilibrium or a chemical reaction, if we talk about this particular chemical reaction, can be your simple oxidation reduction reaction. So, we will just simply see one of the example where we can have the corresponding oxidation reduction reaction, where the oxidation states of the species will change from one particular oxidation state to the other particular oxidation state. So, we will come back once again for the equilibrium which is happening between the corresponding acids and bases, and so many things we can calculate out, so many things we can understand from the typical acid base reaction. But if we think of considering another equilibrium where a redox reaction is taking place and where we can have the electron transfer reaction. So, we can have the electron transfer reaction. So, here we have taken one particular example, that means H3AsO4, sorry, this is AS is smaller, S is smaller S. So, is the arsenate ion. So, AsO4 3 minus, that means H3AsO4, which is reacting with iodide ion. So, this iodide ion reaction with iodide ion in acidic medium can take place through the formation of a corresponding this is in the +5 oxidation state and this is in the +3 oxidation state, that means arsenic center. So, the arsenic center is getting reduced. So, this particular one will be, therefore, we are getting that this particular center is reducing. So, this is functioning as an arsenic acid, this H3AsO4. So, arsenic acid is functioning as an oxidizing agent. So, 1:3 reaction, 1 mole of this is reacting with 3 moles of iodide ion, producing a triiodide species. So, what is happening over there? So, iodide, 2 of the iodide ions are oxidized to form I2, and that I2 when reacts are attached to the third I minus, forming I3 minus. So, this can be considered as a very good example of chemical equilibrium, where we visually understand or visually we can see how far the reaction is going from left to right, or if we start from right or right to left, where the equilibrium stands. So, if we have these species, because we are not considering these protons, the protons are always there. So, if we consider the one species like A plus B producing C plus D, so we will be able to write down a corresponding equilibrium constant for this particular equilibrium state. And the rate of the reaction, basically two things we will be considering: the extent of the reaction, how far it is moving from left to right, that can again be judged from the corresponding K value, the equilibrium constant value, and other thing is also how fast that particular equilibrium is reached. So, the rate and extent to which the reaction proceeds to right can be followed by monitoring the color of this triiodide ion, because triiodide ion is nothing but the corresponding attachment of the iodine molecule to the iodide ion. So, triiodide ion is red brown in color and visually we can see it nicely. So, the formation of this, so through this reaction from left to right, if you are able to produce large amount of I3 minus, which is colored, visually you can detect by your eyes, otherwise you can spectrophotometrically determine the exact concentration of this I3 minus due to the reaction from left to right. So, if we consider the same reaction from the other side, that means from the right to left. So, from the right to left reaction is the reverse one. So, this will be reacting. So, the reverse one is reacting and producing this one. So, we can start from, if some reaction is not going from left to right, say 90%, if we are going say about 50% or 40% from left to right, what we see that for this particular reaction also we get something where these are present, but not that much of I3 minus, which is strongly colored, is present. So, this particular, so the color of this I3 minus, because in the previous case this color is developing from a particular reaction condition, we are not considering that the left hand side, the solution mixture, the reaction mixture is colorless. It can have some faint yellow color also, but on the right hand side you have a dark red thing which is being produced at the iodine elimination. So, that we will also consider when we will be talking about the corresponding redox reaction in terms of the corresponding iodometric titrations. Okay. So, is a well known and well established analytical procedure where we consider the corresponding iodometric reaction where iodides are oxidized to produce iodine. Simple copper 2 plus in the solution in acidic medium can produce iodine, and that iodine which is formed in the reaction medium can be titrated by a solution or a standard solution of sodium thiosulfate. So, that we will find in some of our future class, that how we can utilize this particular chemical equilibrium for iodometric titration. So, this particular thing, so if we have two species on the left, that means A and B, and on the right you have C and D. So, what are the corresponding effect, that means the color change, what is happening over there. So, that is why all the analytical chemistry thing, that means whatever we get, so that particular thing is dependent on the corresponding color formation or the disappearance of the color. So, solution of same color intensity, that is same I3 minus concentration, can be achieved by starting from right hand side as well. So, if we go from left to right or from right to left, at equilibrium we will be having the same solution, the same colored solution when the equilibrium has been reached. Okay. So, let us see how this thing can happen. So, this is the thing, that means the typical example from those color reactions from the beaker. So, what we find, that is a very interesting thing, that how you get this. So, these are the thing, these three beakers for the first type of reaction, and the other reaction is for the other three. So, if you either you go from left to right or from right to left. So, this is the corresponding material what we are getting, that means the triiodide formation over there, and that is the thing, that this triiodide is reacting with that of our corresponding arsenic acid, one of the arsenious acid, and forming this final product like this. And in other case, see, the iodide things are not there, but some of the real colored thing is that when we reach the corresponding equilibrium step, we basically get all the species what is present, that we have seen that in your solution you have this particular species, that means H3ASO3, I3 minus, H3ASO4 and 3I minus. So, at the beginning when we are not having the triiodide species, both these two things are colorless. So, when you start from right hand side, both these things are colorless, but when you get this from the triiodide, if only this triiodide ion, so triiodide ion is strongly colored. So, other things what is happening, so at the equilibrium when we reached from any of these sides, from left to right or right to left, both combination of solutions thus produce the same final solution, that means the final equilibrium state. So, this particular equilibrium state what we are reaching from this side or the other equilibrium state from the right hand side, we are getting same solution. So, when the equilibrium is reached, we should be very much careful in knowing that particular thing, that how this particular final condition we are achieving. So, final position of the equilibrium where we are, suppose we are going from left to right, so a 30% of the reaction or a 40% reaction or a 50% of the reaction, A plus B, 50% of A and 50% of B is reacting to give you 50% of C and 50% of D. So, is independent of the root of the equilibrium state, that means which direction and which way it is going is independent of that particular route, but we are reaching these two final solutions somehow. So, we were going from one particular way. So, the equilibrium for this particular reaction is achieved and we get all these things in a possible way such that we can apply the principle of Latellier's. The Latellier's principle is telling us that, talking in terms of the corresponding position of the equilibrium, and the position of the equilibrium can shift in a particular direction to relieve any stress on the system. As we all know that if we change the particular parameter, that means temperature, what we see that a particular temperature or pressure, if one of the products of the reaction are gas, that means the pressure is relieved from there and the temperature is dependent on your exothermic reaction or endothermic reaction, the equilibrium can be achieved from one side to the other side. Suppose the metal ion is reacting with some anion or the ligand, one color reaction can take place. So, if that particular reaction is endothermic, if we cool down the solution, so more and more of these things will be forming. So, this principle, all you know that the total concentration of the reactant and products will be dependent on the mass action effect. So, this particular mass action effect therefore is controlling that particular equilibrium, which is a dynamic process. So, if we change the temperature and pressure, only thing that we can just change the position of that particular equilibrium, that how much product is forming. So, temperature and pressure is basically we control for a particular type of reaction. Suppose your ammonia we are forming from reaction of nitrogen and hydrogen. We all know that that particular reaction is taking place at a very high temperature and pressure. But if we can consider at a very high temperature only and pressure is the atmospheric pressure, but still some amount of ammonia definitely will form, but which is not very high, the concentration of the ammonia formation is not very high. So, that is why the Haber process, which should be in the industrial process and which is also economically viable, is used for the production of the ammonia, where both these two parameters, that means the temperature and pressure is applied, such that your most of these hydrogen and nitrogen can be converted to your ammonia solution. So, now we can think or we can talk about the corresponding equilibrium constant. So, if we can have a particular reaction, how we can consider about or how we can talk about the corresponding Ka value. This we will be considering as the equilibrium constant, and which is therefore can have for any simple reaction that we can have more than one equilibrium. Suppose we can have H plus and A minus forming H A, and similarly H plus is reacting with a simple base forming H B plus. So, these two, that means this H plus and these H plus are common, but we can have two different equilibria, where one is the corresponding conjugate anion, that means it can be your conjugate base, it can be your acetate ion from acetic acid, or it can be a simple base like ammonia, trimethylamine or triethylamine. But so, you have a base and you have a conjugate acid of a particular acid, which can function as a base. So, these two common species can have, and we can have a simultaneous equilibrium or a competitive equilibria. Competitive equilibria. So, that we will consider in terms of the corresponding Ka values. So, for a very basic or a very standard reaction of this AA plus BB producing CC and DD, where K is the equilibrium constant and sometimes K is written as Ka, A stands for the corresponding acid. And if we consider these, the concentration of C times the number of moles, concentration of D times the number of moles D, and in the A for the case of this A also. And for B also is powered by the corresponding moles, we get the K. So, at equilibrium, just now what we have seen, the corresponding reactions of triiodide, iodide, arsenic acid and the corresponding arsenous acid. So, we get these all four species are present together, but how far this particular reaction will be intense depending upon the concentration of I minus, I3 minus, that will be dictated by the K value, which will tell you that how far the equilibrium can go. So, concentrations of pure solids and liquids are taken as unity, because pure solids and pure liquids will not interfere over there, and for more accurate purposes activities of the species should be used. So, that will give rise to the corresponding K value, and that we will see in our next class, that how we can propose and how we can establish a particular equilibrium value for the simple acid base reactions. Okay. Thank you very much.